we move into chapter 10. From chapter 10 we start to study about frequency response. Okay. Before chapter 10 we didn't analyze about any frequency dependency. From now on we will study about frequency response. But to cover that frequency response materials, what we want to do is review some important concepts. First concept is Laplace transform. We learned this Laplace transform from EE 202, I think 202. Okay, Laplace transform is, by definition, we convert time-dependent function ft into frequency-dependent function fs, and s is complex number. Okay, and f is also complex number. So this time-dependent function ft becomes complex number function. Okay, by doing Laplace transform. Okay, Laplace transform of some function ft. If you do that, then as a result of the Laplace transform, you have this. So in mathematics, the Laplace transform of any arbitrary function ft is defined as this way. You integrate that time-dependent function ft over the time. You integrate, okay, this function s function minus s is complex number, but that is frequency information. Okay, t. You multiply your time-dependent function into exponential minus st, and you try to integrate from current. But current, we just care about current just right before the current. Minus means just right before the current to the future. Future means forever. Okay, until the universe disappears. Okay, that is infinity. We integrate all time function. Then if we integrate all time function, and in the end there is no more information about time. In the end you will have some special complex number function, okay, f, but that is the function of complex number. Okay, that is the definition. So for example, if we have impulse function for ft, if the ft function is an impulse function is look like this one. Okay, impulse function, then that becomes one step function like this, and then 1 over s is the, I said, the complex number, and lamp function is t, 1 over s squared. Okay, decay is exponential format, and then 1 over s plus sigma, and sigma is, let's see, s in general is defined as sigma plus j omega, and sigma is kind of the real exponential behavior described, and omega describes the frequency of oscillatory behavior. Okay, so if we have decay function ft, it becomes 1 over s plus sigma. Now these two are most important, sine and cosine. Sine, cosine has only oscillatory information, no decay information. Then if we do that Laplace transform, then that becomes omega divided by s squared plus omega squared, or s divided by s squared omega squared. Okay, and either way we can have decay plus sine or decay plus cosine, then the sigma information is included. Okay, included. And I think I made a mistake. This is not alpha, this is sigma. Okay, sigma. So the Laplace transform is used to transform some complex time-dependent function, okay, a function into a complex variable s-dependent function. By doing this way, we can easily analyze certain circuit, okay, as a function of frequency. instead of the analyzing as a function of time, the transmission or input-output signals, it's better to understand the frequency dependency. So if we want to do this, usually we use it Laplace transform. And another important transform operations is time differentiation and time integrations. Okay, so same way, if you do that Laplace transform of some function ft, but that function now is a differentiation of the function. Okay, if you do that, you will have, of course, fs. Okay, you will have fs. S is the complex number, so function itself is complex number. But if you do that derivative, s here is coming out. Okay, s times fs. Likewise, if you do that, the integration function ft. Okay, integration, then same way that will come out fs complex number function, but in this case divided by s. Okay, divided by s. Okay, so using these properties, we can analyze some time dependent components resistance. It's because the signal current is time dependent and voltage signal is time dependent. We can convert that situation into S domain, okay, frequency dependent domain. And same way for capacitance, inductance in time domain, we can convert into S domain. But the conversion, it depends on the initial condition, but suppose initial condition is ignored, then the conclusion of this Laplace transform of resistor R, inductor L, capacitor C will be resistor, for example, resistor R is in ohm in time domain. If we do the Laplace transform, their impedance will be R in ohm, okay, ohm. And if you do that Laplace transform of the inductor, and they will be S times L. Of course, the dimension is ohm because we are talking about the impedance. Okay, if we have capacitive component, okay, capacitive component, then that will be 1 over SC. Of course, the dimension is ohm. Okay, so we in the real circuit, we try to do replace resistance to R and inductor S times L, capacitance 1 over SC. We express all these three components in terms of the impedance amount. Okay, impedance amount. Okay, L and capacitance. So using that concept, we can analyze further. Another review point we have to understand is transfer function. So transfer function Hs is function of S is complex number. So Hs will be complex number, and that is defined as output signal, but of course in S domain, to input signal S domain. Okay, and Ys is as a result of Laplace transform of time dependent function. And Laplace transform of time dependent function. The ratio will be transfer function. So transfer function is something like a gain. Okay, gain, output signal to input signal. Okay, gain. So sometimes some textbook they express H instead of using H, they use T, S. Okay, if you only think about voltage input, voltage output, there will be voltage output to voltage input. Okay, but those functions are complex dependent. Okay, all right. So if the complex frequency has two information, sigma and j omega, yes, we can replace like this way. But what if S equals 0 plus j omega, which means sigma equals 0 means There is no decay function, only oscillatory function. Then we usually try to think about the amplitude of these ratios by using, instead of S, you plug in j omega divided by input j omega. Okay, so that is the transfer function. So we'll analyze the circuit using this transfer function. Right. Another review point we have to understand is high pass filter. High pass filter means high frequency. In terms, if you plot this graph, the performance of this circuit as a function of frequency to transfer function. Okay, transfer function. T is transfer function. So transfer function, in this case, transfer function was defined. Okay, output to input. Output signal terms of j omega to input signal v input. Okay, j omega. If you plot this value, okay, for this typical high pass filter circuit, they follow this performance. Means a lot of high frequency ranges. Okay, high frequency means gigahertz, terahertz. Okay, a lot of high frequency ranges. Their transmission is like a 1, right? 1 means output signal becomes input signal. The ratio is close to 100%, right? There is no loss, but low frequency zone, there will be a lot of degradation. So ideally speaking, when DC component, it will be 0. When you have high frequency, it will be 1. But how do you connect those two lines? In general, those two lines are connected using some special natural behavior using exponential function. But more details we can study. But here the point is how we define special point. Before this frequency and after this frequency, yeah, we have to define what is the critical line. So conventionally we define when the value becomes 1 over root 2. Okay, this value becomes 1 over root 2. When omega equals omega 0. This time exactly the value is 1 over root 2 situation. That is about 70% of the signal. In that case, we define that as the critical or cutoff frequency. Okay, that cutoff frequency. If we analyze this simple high pass filter, okay, high pass filter, so we convert into the S domain, right? This is V input and voltage output. R is R, capacitance becomes 1 over SC. Then you can calculate your transfer function ratio. Okay, will be my total impedance is 1 over SC plus R, and the voltage drop is only across the R, so R. And you can simplify this equation by doing S divided by R, S divided by R, top and bottom. Okay, then that becomes S is gone, R is gone, and S is left here, and S here, and S there. So RC, the switch 1 over RC, and R is cancelled, and S. So the form is S divided by S plus something. Okay, so high pass filter, their transfer function looks like S divided by S plus something, and this something is also in terms of dimension is frequency, because S was frequency plus frequency. Okay, this frequency we define omega 0 or cutoff or omega 0 frequency, and if you calculate that omega 0 is 1 over RC. Okay, 0 is 1 over RC, and RC is the value of R and C. Okay, so sometimes we call this RC as 1 over tau, and tau is time constant. If you multiply ohm and farad, then you will have sec information. And if you plot this graph in terms of the log scale, okay, in terms of decibel over the log scale frequency, and you will have something linear line. And when omega equals omega 0, the point will have about 3 decibel decay. 3 decibel came from 3 decibel came from when you have 1 over root 2 value from the peak, okay, then that value is 20 log 1 over root 2 becomes about 3 decibel. Okay, so that is 3 decibel point from the peak. So that is, as we said, omega equal omega 0 case. And if you plot this line, linear line, the slope looks like about 20 decibel per decade. In one decade difference, there will be 20 decibel differences from here to here, 20 decibel difference. And here is a 10 difference, which is one decade. Or if you convert that 20 decibel per decade into other scale, for example, octave, that will be 6 decibel per octave. I think octave is twice the frequency difference. Then you will have 6 decibel difference. So slope is 20 decibel per decade equals 6 decibel per octave. It's the same concept. All right. And next review point is low pass filter. Low pass filter is CMA, lower frequency. Most of low frequency will pass, and higher frequency will close to 0. But how do you define the special point? Omega 0, so 1 over root 2 point. And if you plot this linear scale into log scale, you will have some flat and suddenly go down with the linear line. That slope is minus 20 decibel per decade or minus 6 decibel per octave. Okay, and that point is cutoff frequency, omega equal omega 0. And here the thing is, you switch, if you compare with this, the capacitance here, resistance here, but now switch resistance and capacitance. So for this transmission, the transfer function case, total impedance will be R plus 1 over SC, and your voltage output here across only 1 over SC. If you simplify this equation becomes omega 0 divided by S plus omega 0. Okay, and omega 0 by definition was 1 over RC, which is the 1 over tau, okay, time constant. Okay, and the characteristic is same as the high pass filter. So the general form of transmission, transfer function is this way. Okay, compared to high pass filter general form was this one, S divided by S plus something. Okay, but here is something divided by S plus something form. Then that is the low pass filter transfer function. So we, as I touched a little bit about RC time, that is called the RC time constant. Okay, because R times C is the dimension will be sec. Okay, so which is time. So some number. Okay, and let's call that is tau, some critical RC time constant. So cutoff frequency has a relationship with 1 over tau by definition, because we define tau as R times C. Okay, so tau defined how fast they increase the signal to the maximum, how fast they decrease into the zero signals. Okay, usually the nature follows the exponential nature. Okay, so natural response, they follow natural response. Okay, so most of case we are using exponential functions, log scale, natural log scale functions for this calculation of cutoff frequency and RC time. Another thing we want to review is common emitter amplifier. Common emitter amplifier. If you remember common emitter amplifier, we try to add some capacitance, right? Coupling capacitance coupling capacitance, bypass capacitance. Alright, so there is bypass capacitors. Okay, so if you remember the bandwidth of the transfer function, in general, lower frequency degradation happens because gain will be false off because of the effects of coupling and bypass capacitors, right? External problem. And after certain frequency, higher than certain frequency, usually they will false off because the internal problem, this internal problem, or external problem. Okay, internal problem, or external problem, okay, no problem. All right, now let's move to subchapter 10.11, low frequency response of CS amplifier. So common source, okay, common source circuit. This is common source circuit in time domain. In time domain, if you remember, we need a coupling capacitance for the input signal, coupling capacitance for output signal, and bypass capacitance, okay, here, to make it a virtual ground. This time domain circuit we can transform into Laplace. Using the Laplace transform, we can turn into S domain, okay, S domain. This time domain becomes S domain. When you convert the component, the voltage, time dependent voltage signal, we can express, that is the complex function, but function of S. And resistance becomes simply resistance. Capacitance you convert into the impedance, which is 1 over SCC1 here, and here is 1 over SCC2, and here is 1 over SCS. And other resistance will be same. So we using the Laplace transform, we convert time domain circuit into the S domain. Right, now we want to calculate transfer function, overall transfer function, which is what will be your ratio between output signal to real input signal. Okay, to calculate this transfer function, we can think about three different the part. First part, we can think about your signal goes into this gate point. So first we calculate VG to V signal ratios, and next stage is we try to calculate what is the ratio between ID divided by VG, and last, what will be your voltage output to the ID. So if you look at this carefully, VG will be gone and ID will be gone. In the end, you have V output to V signal ratio, which is what we want to analyze, okay, which is transfer function. So first, focused on the green color area, we want to calculate voltage at the gate, okay, if we have voltage signal here. So convert into the S domain. So for this case, how do you calculate the voltage output here? So voltage output at G point will be V signal S times total impedance. Total impedance is signal plus series connection, so that is another impedance, SCC1, plus this is connected in series here, and that is connected to series here with the two component, which let's call that is RG, which is the RG1 parallel RG2. Okay, these three impedance are total impedance, and voltage output here VG is only across these two resistance. So that is RG. Okay, and RG, I said RG is just parallel of RG1 and RG2. Okay, so if you simplify that equation, then in the end we have this special form, and this form is easy to understand. So voltage gate to voltage signal will have some constant number times S divided by S plus something, right? And here square is kind of constant amplitude, okay? Gain. So if you don't care the capacitive component, resistance, the voltage output here will be ratio between total impedance and across this, right? So it makes sense. That will be RG divided by RG plus signal. Okay, and if you simplify this equation, and star becomes some in the end, star will be the frequency information, okay, which is the some, let's call that some special pole 1 frequency, okay, omega p1. And if you remember, that will be 1 over RC component, right? RC. And C is, we are talking about CC1. So C is CC1. And R case, if you look at this circuit again, R has two things. Left side R signal, right side RG. And they are connected in series. So in the end, you have to add those two resistance together. Okay, one is the signal, one is the gate resistance. So you have this equation. So we have two important information. From this first component, you got first stage, you got gain G divided by RG plus signal, and first frequency is 1 divided by RG plus R signal times CC1. Okay, next. We want to analyze next stage, okay, in terms of the second here, ID divided by VG. Okay, and ID divided by VG, if you remember Ohm's law, V equal IR, so I divided by V means this, and V is gone, R is over here, so 1 over R is kind of transconductance, right? Transconductance. So in the end, you will have some information about transconductance times some filter information. Okay. So the conclusion is, okay, of course we can analyze everything. If you analyze carefully, then in the end you have two information. So the ratio is the gain, okay, gain term, and S plus omega Z and S plus omega P2. A2 is, as I said, the ratio will be transconductance. So A2 is kind of transconductance information, which is GM. Okay, and omega P2 is something like 1 over RC information. 1 over RC information. Okay, C information. C is, we have coupling. Okay, capacitance, and this capacitance share the resistance in parallel to RS to 1 over GM, right? So you consider that is the 1 over GM resistance and RS resistance, that is omega P2. Omega Z is 0 frequency, that is a little special case, okay, but down here to some cases maybe we can have same value of resistance, okay, because that is the impedance. The impedance amount will be same as this amount, but special case. Okay, so that is Z means zero frequency. Zero frequency will be 1 over R C. R is S value, C is S value. In these special frequencies, and these guys to eating up all information, so their output signal will be close to 0, something like this. Okay, so two frequency information we can get omega P2, omega Z. Okay, P2 Z. And last one is transfer function is for voltage output to ID current. Okay, so last stage here, using this last stage information, okay, we can analyze. But conclusion, let's look at the conclusion first. If you remember, this is voltage divided by ID will be something like resistance information. Sorry, the resistance R. Okay, R. It will be resistance. So you will expect the result will be something like resistance information times some low pass filter, no, high pass filter components like S plus star. So scale was resistance component, and resistance, if you look at only resistance, these two resistance are parallel, so that will be RD parallel RL amount, and the star will be, we define omega p third frequency. Okay, third frequency will be 1 over C term. C is coupling 2, and this coupling capacitance share to the left and right. Okay, so you have to add two resistance together. Okay, together you have to add 1 over RD, 1 over RL. So that will be the final form of this pole frequency omega p3. Okay, and the gain will be this one. So if you add all these three things together, okay, first term is green color, first stage, and here's the next stage we try to analyze, and last stage, okay, 3. So final transfer function will be first green information times red information times blue information. So there is three things: total overall gain, green components and red components, GM, and last component, which is parallel of those. And first high pass filter information, and second high pass filter, and third high pass filter information. All these three terms are multiplied together. So that is the final form. And overall, we can understand that frequencies will usually happen. Okay, the major frequency loss will happen. Okay, major first cutoff, okay, will happen usually because of the second fall. Second fall is FP2. FP2, if you remember, FP2 was related with this bypass. Okay, bypass. So bypass frequency is dominant. Okay, first dominant, and next usually and third or first or the zero frequency. Sometimes these two things are about same, but in general the lower 3 decibel frequency, okay, lower 3 decibel frequency is about same as, roughly you can say that is close to P2, which is due to the bypass capacitance. Okay, bypass capacitance will define the first cutoff like this. Okay, all right. So we can understand those circuit. Okay, three components. If you remember the green color, red color, and blue color, three stages. From the first stage, if you look at the first stage, yes, the coupling capacitance, and they have left side signal resistance, right side gate resistance, and looks like RC component is C is sharing RG plus R signal, so that is first time constant from the green color information. And red color, from the red color, we can also think about what is the time constant. So look at the CS share the two resistance, okay, as a parallel concept. So you do parallel of these two resistance times the bypass capacitance. Last the blue part, okay, last blue part section, okay, coupling capacitance share the left side drain and right side resistance here. So that is the RC time constant here. So there are three time constant involved: tau 1, tau s, tau 2. So in general, to calculate the real the lower 3 decibel frequency, we calculate the 1 over 2 pi, because we want to calculate the frequency in terms of hertz. Okay, in terms of hertz, that is, okay, you calculate first frequency plus 1 over, and the bypass frequency plus 1 over tau 2. Okay, roughly we can add these three components, but as I said, this is most dominant. Okay, this is most dominant. All right, so this is the summary about the whole lower 3 decibel frequency and 0 frequency, and some FP1, FP2, FP3 information. Okay, so this is the some overall simplified circuit, okay, in S domain, and we can simplify this way. So first we calculate what is the ratio between voltage G gate to voltage signal. Then we calculate the drain current to the voltage gate, and then we calculate voltage output to drain current. So three stages. From each stage analysis, you have this information and this information. So you have the gain information here. Okay, gain information. Omega A2, A1, and A3. Okay, and frequency information. Okay, P1, P2, P3. P we call pole frequency, and omega 0, 0 we call zero frequency. Zero frequency is related with this purple color component. Okay, all right. Example 10.1. We want to solve the real numbers using the real numbers. So all numbers are given, and it is required to have lower 3 decibel frequency 100 Hz. 100 Hz. So FL, we want to design 100 Hz. Okay, and that the nearest break frequency be at least a decade lower, nearest break frequency. So which means this is 100, and nearest one we want to have 1 decade lower. So if this is 10, we want to have 1. If it's 100, we want to be here 10. So 1 decade lower. Okay, at least 1 decade lower means that one. So roughly this frequency 100 megahertz, 100 hertz is close to FP2 information, which is due to the bypass information. So coupling capacitance we can calculate from that. Okay, from that 1.75 microfarad. FP1, FP3 from this problem, they said 1 decade lower means instead of 100 hertz we want to have 10 hertz. So omega P1, omega P3 values are 10 hertz. Okay, based on 10 hertz. So you can calculate based on all this information. That is 3.3 nanofarad and 0.53 microfarad. And zero frequency, since we know that the RS value and CS value we just got from here, so if we multiply, that is 9.1 hertz, and 9.1 hertz is about same as 10 hertz. Okay, and then we can calculate also mid-band gain. This is called AM. Mid-band gain has 3 components, right? From the green color signal, you go down about this scale, and then the middle part and transconductance times the last part is resistance, up resistance. Okay, and that is about 10. Okay, and if you have these values fixed, and then you can calculate the FP1, FP2, FP3 and 0 frequency, and the final FL, lower 3 decibel frequency, we can roughly say that will be close to P2 because the coupling capacitance is dominant, okay, which is the true. 334 Hz is way bigger than 8 Hz were these values and these values. Okay, so lower first cutoff of this performance, which is the 3 decibel degradation, happens at FL, which is close to FP2. So today